Thank you, Robbie. Right, good morning, everyone. Quite in line with the usual ICFP list of topics, I'm going to tell you about hacking computational geometry. And as most of you probably know, computational geometry is this field of computer science that deals with algorithms for efficient solutions of geometric problems, such as those we find in navigation, data clustering, computer graphics, and many others. And the most common species you have to deal when you are dealing with computational geometry are polygons. Well, some of them might be small and neat, some of them might be medium-sized, and some of them might be totally crazy. But there is at least one thing that all of them have in common, which is not entirely obvious. Polygons turn out to be trees. And just like trees, we can grow them. And just like trees, we can also trim them. And if at this point you start wondering what does it have to do with functional programming, let me give you a teaser. The fact that they are trees also allows us to use QuickCheck to test their properties and also the properties of the procedures that manipulate with polygons. So my personal journey into the fascinating land of computational geometry started here. That's UCL, the main building with the famous dome. And this is the Department of Computer Science with my office in it. So one day, around January, our departmental tutor came over to my office and asked me, would I like to run a scenario project for students? And that idea sounded like fun, so I answered, sure, why not? And then I asked, well, what is scenario project? And he gave me the requirements. So that's a regular thing which UCL runs for second-year undergraduate students. It makes an emphasis on the teamwork. It takes 1 week, during which the students don't attend any other lectures, that just hack or try to solve some problems. That particular project, since it's the Department of Computer Science, should have involved some mathematics and some computer science. It should have been relatively easy to assess, but challenging to implement for the students. And this all was fine, except for the last point. That should have been delivered in about a month. Well, after fighting the initial panic attack, I took a look at my bookshelf in the office and found this great book, Computational Geometry, Applications and Algorithms by the Berk & Company. And this book turned out to have an amazing amount of really, really nice problems, each of which could have been turned into such a scenario project. So let me tell you about one such problem. Assume we have a gallery with precious pieces of art. And indeed, we want to keep this gallery safe, like we keep our programs safe, but this is a real world, so we just hire guard. And this is an elder guy who doesn't like to move around, so he just looks around but doesn't move. And he obviously cannot see that second corner, so we hire another one. And at this point, we are not entirely sure how many guards we need to cover the whole gallery, so we hire a whole bunch of them. Well, clearly that is sound, but probably we can do better. And here's the question, how many guards do we really need? And the answer indeed depends on the shape of the gallery we've got. So the gallery, think of it as a simple polygon, for now without any hole. So if our gallery is something like that, we can just hire one guy and put him anywhere, like in the center, and he can see everything. If our gallery is something more convoluted, well, let's see. Let's hire one and put him here, and the yellow part is what he can see. So this covers the second part, so 3 should be about enough. Generalizing, the question is indeed, for a given gallery, represented as a polygon, how many guards in the most optimal case we need, and where should we put them so they could see the entire interior? And you can recognize an optimization problem here. And as most interesting optimization problems, this one is NP hard, which makes it so great for the competition. So let's just try different heuristics, different approaches, and see which of them works well for specific classes of galleries or the polygons, such as the enterprise. Turns out that we need only 5 guards in red shirts to guard this one. And the polygon is actually quite large. It's already 58 vertices, but 5 guards should suffice. So the idea was to generate a large number of large galleries, give them to students, but different galleries have different features, so presumably you can optimize because of that, and see how well they perform. And this is what stated our agenda. First of all, we needed to have a generator for these problems. Obviously, we don't want to encode these polygons by hand. We want to generate them, and we also want this process to be highly customizable. So different galleries would have different features. Some of them would be convex, some of them will be rectilinear, and etc. Second, we don't want to grade solutions manually. So we want to have ideally something like a web server, which runs some geometric checking algorithm and makes sure that solutions the students submit are sound and optimal, so they can be compared to each other. So that requires some number of geometric hacking and also some amount of not so sophisticated web hacking. Finally, and most importantly, all this should work. So this server will have to run for the entire week. Students will be using it. They will probably even abusing it. And we will have to make sure that it doesn't crash because we don't want to make them unhappy. So this is our agenda. We got 1 month, and for that reason, we pick a language which is suitable for rapid prototyping and went with it. So in the rest of my talk, I'm going to focus on these two parts of what has been done, because they are, as it turns out, related, and moreover, they're related to the fact that polygons are trees. For the implementation of geometry and the web server, please refer to the paper. So how do we generate the problems? Our problems are polygons, and we want them to have different features. Well, let's just grow the polygons in the following way. First, let's figure out what kind of features we want to have in a polygon. Like here, all our features are represented by this small set of primitive polygons that are rectangular. And we are going to build our larger polygons out of rectangular polygons, which will ultimately get us the rectilinear polygon. This is how we start. Let's pick a random polygon from them and call it a seed. This is how we plant our tree. Now let's grow branches of this tree. Let's pick a segment on the perimeter of the seed, pick another primitive, scale it, rotate, and attach it. And this process actually is quite generic, so we can repeat it several times, pick a segment, pick a primitive, attach, rotate, do it again. So we repeat it several times until we are happy with what we got. So this is the whole process, and it's easily summarized in a number of steps. So first step is pick a primitive polygon we want to make a seed or we want to attach. Next, locate the position where we want to attach it to. And finally, scale, rotate, and attach it, also checking that we haven't introduced self-intersections on the way. So if it happened, we just roll back to the step 1 and repeat. And this process is repeated as many times as we want in order to get very large polygons. So this is a process which doesn't really depend on the shape of the polygon. So we can make it to an abstract library, which in Scala can be implemented as a trait like this. And you can see some small amount of hierarchy here. For example, for seeds, we can just provide a list of polygons to be planted. For primitives, so here it's also implemented as a bunch of lambdas, so we could tweak some scaling parameters of what we are going to attach. Locate is a function which defines how exactly we pick those segments on the surface of the polygon that we are growing. Also, to tweak the frequencies, we provide these two lists to make sure that some polygons are chosen more often than others. And finally, we define the number of generations which all this process is going to be iterated. So again, it doesn't mention any specific polygons. Square, triangles, you name it, you can instantiate it and get something really, really funny. Like this, or even like this. So we were quite happy to play with it, generating a large number of these inputs and preparing to give them to students, at which point we realized, look, we have a polygon generator, so let's put it to some good use. Let's put it to testing. So given that Scala is a functional language, it comes with quick check implementation, which in Scala is called ScalaCheck. So this polygon generator that we already had, we just plugged it into ScalaCheck and tested all geometric machinery that we had implemented in our check-in server for that moment, such as a triangulation. It's not a particularly difficult geometric procedure, but it's surprisingly difficult to get right if you are writing it according to the textbook definition. So here are some basic properties which I'm not going to state. So some that has been tested, some bugs were discovered. More interestingly, we had them to implement an algorithm for visibility construction. That's something I'm going to elaborate a little bit further. Turned out to be very tricky, also got tested, found plenty of bugs. Finally, the main visibility checker, which picks all these pieces and put them together, even more bugs. And finally, just to make sure that this is all coherent, we have hacked ourselves several textbook solutions for the art gallery problems, such as the standard one by Fix from 70s, and made sure that these are indeed delivering the correct solution according to our checker. So all this is nice, so all this can be visualized, and it's really easy to assess. So, but how well did it work? So what bugs were exactly found? Well, turns out that once you program geometry, you inevitably run into floating point computations, and those are nasty. So it's quite easy to choose the wrong epsilon and mess things up, and things just go wild. So we found quite a few bugs, I think more than 20, due to inaccurate treatment of the floating point numbers. A slightly smaller number of bugs has been found due to the fact that we simply misread the textbook descriptions of the algorithms, because those are usually formulated in pseudocode, they make some assumptions, and when you translate it into something like Scala, well, bugs appear. And this is my favorite. So 2 bugs were found in the textbook algorithm itself. So I have to say this is not the most commonly taught textbook algorithm. So you probably don't encounter it in a standard textbook on computational geometry, but this is the first one which comes out when you Google for something like visibility checking. So everyone keeps referring to this algorithm, which is 30 years old. We did not manage to find many implementations. There is just one. It's in C++, and I'll tell you a little bit more about it. So this particular implementation has been also assessed by one of our colleagues, who was so fascinated by the fact that we can now generate large polygons. He just generated a bunch of them, and he tried to run the procedures from this state-of-the-art Seagull library, computational geometry algorithms. This is a very big library. It has been developed for more than 20 years. It's very, very hardcore C++, and it doesn't use the floating point arithmetic. So it works with what's called exact arithmetics, which is very difficult thing to work with. And what we were considering initially a bug, and we were quite happy, and we wrote to the authors of the Seagull library, turned out to be more like a badly documented behavior. So we linked their algorithm against the floating point model, which was not supposed to happen, but that hasn't been documented, so they fixed it since then, which I consider to be a good thing. So let me tell you more about these 2 bugs that we found in the basic visibility algorithm. This is what the algorithm does. It takes the polygon, it takes a point within the polygon, and it builds the visibility area, which in this picture is yellow. That can be that this point, this guard, can observe without moving while standing in his position. So the gray parts are not visible. So the original description, as I said, is 30 years old, and it has quite a number of simplifications. And when you try to transfer it to the implementations, well, some interesting things are being discovered. So this is the quick check this quick check style property test which discovered the problem. So let's see what is happening. It generates a bunch of polygons. So here's the lambda which is responsible for that. For each polygon, we take all its vertices and put a guard into each of these vertices. And for each of these guard, we build a visibility polygon. So indeed, all these should be more than enough, and this should cover the whole area. But what was tested is, in fact, that each of these visibility polygons lies within the original one. Specifically, if we take all edges of all visibility polygons using this for comprehension, we should check that we are checking that every single of these edges is contained as a segment in the original polygon P. So that should be easy enough. Let's see what we got. Well, we got this. This is a large polygon with 260 vertices, which has been generated using our framework. And there's clearly something not right here. Specifically, we've got magic guards that can see through the walls. So this is not supposed to happen. Well, so now as the bug is identified, it needs to be wiped out. But this is a rather difficult thing to do, because if you think of it, this is a 260 vertices polygon, and this is our input. And now we need to debug a visibility algorithm on this large input. But, well, this is something that QuickCheck knows how to deal with. We need to shrink our input. But how do we shrink it? Well, when we come to the fact that we need to shrink polygons, what in fact we mean is that we need to trim them. We don't want to make the polygons smaller. We want just to cut some parts of it which are irrelevant for this problem. And it turns out that trimming polygons is a very, okay, so it's not entirely non-trivial, but it requires some insight. And the insight comes from the fact how this polygon has been generated. So it has been generated inductively by picking more and more primitives and attaching them to what has been built by that moment. So we can, let's enumerate that process for convenience. And as we were growing this polygon, we could have also built an auxiliary data structure which keeps the dependencies between these primitives. So this is what we call an attachment tree. The attachment tree captures the fact that, for example, the polygon 4 couldn't have been attached to the entire body before the polygon 2. So these are the dependencies between the primitive polygons as they were attached. And it's not difficult to see that if we take any subtree of this attachment tree, reverse the arrows, and then render this tree starting from the root, we will get a valid and connected subpolygon of the original one. For example, if we start from polygon 2 and traverse this subtree, we can also drop some nodes like this to the polygon 3, we'll get this part, which is still intuitively the subpolygon of the original one, and it has the same features. And the same can go for this subtree 1 to 6. We don't need to cover all of it. We just need to cover something which is a valid subtree. And that gives us a very nice and exhaustive shrinking strategy for the polygons, how to minimize our input. First, we build the attachment tree at the same time as we are constructing the polygon, and we just store it with it as a composite data structure. Next, we construct all its subtrees with the edges reversed. And finally, we render all the corresponding trimmed polygons by traversing these subtrees from the root. And indeed, you might wonder whether that was working. And in fact, it did. So that was our failing test case for the bug in the Joe-Simpson algorithm. And this is what it has been minimized down to, which is way more pleasant. It just got 20 vertices, so it's easy to debug. Well, for this specific case study, we also removed manually the irrelevant guards. That was already easy to do because this is a small one and it has been visualized, and that left us with this one Superman. Okay, so I'm not going to go deep in detail what exactly was the bug. So let me just tell you that this Joe-Simpson algorithm is like a plain sweeping algorithm which casts rays from the guard and checks the intersections of this ray between with different edges and nodes, and depending on whether there are some cavities here. So it actually boils down to a fairly large case analysis of different ways of intersecting this ray with the edges of the polygon. And in some case, it's just what happened that this particular check was lacking. I'm not going to explain what exactly it means, but essentially it was screwed up by the fact that these two nodes were aligned. So I wonder how it hasn't been discovered in the original algorithm, but I'll double check, and the pseudocode implementation in the original paper doesn't have it. So we were quite happy. That has been fixed. That has been checked on multiple times, not just on rectangular polygons, but on many others. So we happily released the server and started the competition. So since what I'm presenting in the experience report, this is a mandatory slide with the implementation effort, which is amazingly modest. So the whole geometry, which for the record, we have never programmed before, especially in Scala, has been implemented from scratch and took less than 1,500 lines of code. And about the same amount has been spent on the server's infrastructure, which is nothing particularly exciting. Finally, the testing framework, which was directly built on this geometric primitive, is 350 additional lines of code, which I think is quite nice. So let me tell you a little bit about how the competition went. So we got 94 participants, which were working in 24 teams. And over the course of 5 days, they submitted 2,360 submissions. So the server was running all this time, 24 hours for 5 days. And there was some small amount of concurrency there. So the server was implemented in Akka, and solutions for different teams were processed in parallel. But for the same team, they were processed sequentially. So there would be no denial of service attacks. Okay, so the server didn't crash, but there was one non-critical bug in the server logic itself, which, not surprisingly, hasn't been quick checked. So that was easy to fix, and we had just hot swapped the changes without restarting the server. So bullet dodged. With respect to the solutions, what kind of surprises we could see? Well, there were a few, but most of the teams just took the standard textbook algorithm that you can find if you Google for the art gallery problem, which gives a sound but an awfully bad solution for most of the cases. And then some optimizations were made on these solutions. So that worked well. What we were surprised about is that the team that won the competition actually found a state-of-the-art algorithm published in 2014, which used a set coverage problem as a way to reduce the art gallery problem, and then employs linear programming. So this is a theoretical paper, but the kids took the algorithm and implemented it, I think, in Python, and that worked amazingly well. So that bet all other competition, including those that try to optimize by hand, by rendering the polygons and spending an awful lot of time tweaking the solutions. That happened. This is just a funny slide which has been rendered by one of our PhD students. This is the competition, which has started on Monday at 10 a.m. And it went until Friday at 3 p.m. And the blobs represent the intensity of the submission. Quite amazingly, people were hacking at 2 in the morning, and before the deadline, even at 5 in the morning. And this is the last hour. And someone managed to sneak in the solution 2 minutes after the deadline because the server was permissive, just to be nice. All right, so that was the outcome. And what I would like to take away from our experience is that, well, functional programming also works for computational geometry. So if you want to have something robust, something not trivial, and being implemented in a relatively short amount of time, pick nice language. Scala, I think Haskell will work too. What is more essential for this talk is that if you pick something functional, you also get access to all these nice tools like QuickCheck, and you can QuickCheck computational geometry, which is quite efficient in practice. And finally, the insight that you need to have in order to check something with computational geometry that manipulates with polygons is that the polygons are trees. You can grow them, and you can trim them. And this is all I have. Thank you.
Hello, I'm Matthias Görgens. I'm asking, did you just give people a bunch of examples and they gave you examples back, or did they submit programs that you?
OK, so the question is, what were the problems? Did the students have to submit the code, if I understand correctly?
Yes, right? And basically, if they submitted code, did you use QuickCheck to test the code?
OK, so let me just answer the first. Yeah, I won't have to answer the second. So they didn't have to submit the code. They were free to use whatever they want. Some of them used MATLAB. Some of them tried to use the libraries. For what it's worth, it was a teaching exercise anyway. So if they were supposed to learn the libraries, this is also good. I cannot say that those people who found some fancy libraries got a lot of advantage over those who have implemented that from scratch. And eventually, everyone has submitted text files.
Hi, Wouter Sierstra. So I was curious, did the students know what random generators you were using?
So did the students know what the generator was?
Yeah.
Well, the problems were pre-generated, so they were aware of everything which is there.
Okay.
And initially, but they were quite large. So the largest polygons were up to 500 vertices. So something which is quite painful to do by hand.
Okay, thanks.
So John Hughes, Shalmash and Cubic. One idea that I would be tempted to try when shrinking a polygon is just removing a vertex and replacing 2 edges by 1. Did you try that?
Yes, but that immediately introduces self-intersection if you try to remove vertices.
Well, then you shouldn't remove that vertex.
Well, yeah. Well, the idea is that then you significantly change, let's call, a shape of the polygon. So introduce the edges which were not there. What we wanted to have is the way to make the clean cuts to expose the features which were actually causing the problems, as it was in the example that I have demonstrated. Okay.